Hey, Wildcats. All right, we're going to move on to talking about profit maximization. So this is, again, if you were in class on Wednesday, we started to cover this material, or we covered this material, but maybe rushed it a little bit. So I'm going to do another video covering profit maximization. Okay, so in the last video, we talked about calculating the marginal cost specifically. And so let's go back to Finance 1. Again, we had um, cost functions that were something like the total cost is like, let's see, um, 100 plus 10Q, right? And then our total revenue function was something like 25Q, right? Because we had the price times the quantity, where this is a fee for service type total revenue function, total revenue, not, okay? And so what did that look like? Well, we would start with, 100 and then go up at a slope of 10, right? So that was our fixed cost for, say, 100. Our total cost was the fixed cost plus the variable cost. And this gap here was our variable cost or total variable cost. And then we had our cost function written in, and then we would say, okay, the total revenue function is also a linear function. It starts at 0 because if you do no visits under fee for service, you get no revenue. And so it starts at 0 and it goes up at a slope of 25, right? So it would do something like this, where total revenue goes up at a rate faster than total cost because the slope of the total revenue function was 25 and the slope of the total cost function was 10. And so eventually the total revenue function starts below total cost, but then rapidly catches up because the slope of the total revenue function was greater than the slope of the total cost function, right? Or the marginal revenue was greater than the marginal cost. And eventually the marginal revenue, because it was so much higher than the marginal cost, allowed it to overcome the fact that total revenue starts at a disadvantage as a result of the fixed cost. And what we would find is our break-even quantity, right? And our break-even point where the two lines crossed, that told us that up to the break-even quantity, or to the left of the break-even quantity, was our zone of loss because our total cost was greater than our total revenue. So for all points to the left of the break-even quantity, if you pick some Q1, right, you would have this much revenue and this much cost. And since the cost is greater than the revenue, we had losses. At break-even quantity, the two lines are crossing, so they're exactly equal. So total revenue is equal to total cost, so your profit is 0. And then anywhere to the right of the break-even quantity gave us our zone of profit. So we could draw a line, say, from down here at Q2, and we had this much cost, right, to this point on the line. We had this much revenue at that quantity, and this gap was our profit, right, because total revenue was greater than total cost. So conceivably, this doesn't really tell you where your profit maximizing quantity was. If this was going to be true forever, you could just keep on going this way, keep on going this way, and that gap would just keep getting wider and wider and wider and wider as we went along, right? It'd go wider and wider, and you just keep on making more and more profit. And so this is part of the unreality of a linear cost function, because as you increased your quantity, your costs are going to increase at an increasing rate. And so instead of having um, a cost volume profit graph like this, a more realistic thing is to say something like what we did in the last video, which is 10Q plus 1 over 100Q squared. So it's a small kicker. It might take a little while for it to kick in, but kick in it does do, right? And so instead of having a linear cost curve, reality is a little more like a, um, uh, uh, a exponential cost curve. And so we're going to see something like this, right? So this is our total cost curve. Still have our variable fixed cost, right? And then our variable costs are increasing at an increasing rate. We still have our total revenue function of, say, what did I do here? I'm going to go with 75Q instead. Okay, so doesn't really change anything. So 75Q, just because I did the math a minute ago with 75. Okay, and so what would that look like? That's going to be a line coming out of 0 and going up at a rate of 75 for each Q, right? So total revenue, total cost here on the y-axis, Q on the x-axis. And so linear revenue function, just like we've been dealing with, exponential cost function like we did in the last video. So looking at our old graph here, I'm just change that to 75. There we go. Now I'm happier. Okay. So our costs are going up at a constant rate, but our revenues are going up at a constant rate, but our costs are going up at an increasing rate. So what do we do with this? How do we find where we want to produce? Well, some things are still true. We still have a break-even point, right? Where total revenues are to the left of which total revenues are below total costs, right? So at Q1 here, it's still true, same as before. The total cost line, right, is above the total revenue line at Q1. So this gap represents loss. Now, when we cross the break-even quantity, we'll call that break-even quantity 1, right, we move into a zone of profit where, say at Q2, right, the total revenue line is now above the total cost line, and so we have profit. So everything to the right of BEQ1, right, is going to start generating profit. And as you can see, as I move along, that gap is getting bigger and bigger, right? If I draw another line here, right, you can see that this gap is bigger than that gap. And if I draw another line here, right, this gap is bigger than that gap, right? So this gap represents the amount of profit that we have. So the bigger the gap we have, the happier we are. But notice something happens. I go out to here, and what starts to happen is this gap is now smaller than this gap. And then I could draw another one here, right? I'm going out to the right, and this gap is really small, maybe even like that gap. And then I get to this point where the total cost curve crosses the total revenue curve a second time. And we kind of have a break-even quantity 2, where if we go past the break-even quantity 2, we now have a zone where total cost is once again greater than total revenue. And so past break-even quantity 2 and forward is a second zone of loss. So we have loss to the left, loss to the right, and we have this kind of zone of profit in the middle where total revenue is greater than total cost. And so we definitely want to be in this zone, but we really want to find is that sweet spot where the gap is widest between total revenue and total cost, because again, the gap represents how much profit we're making. So the question is, and we talked about this in class, but the question is, how do we find that spot, right? Well, the answer is fairly straightforward. What we want to do is find the spot on the total cost curve where the tangent or slope of the total cost curve is equal to the slope of the total revenue curve. So that looks like it's kind of right about here, right? If I take my pen, right, I'm going to substitute this in for a straight line, and I bring it up against the curve of the total cost curve, I can bring it up and it touches and makes a tangent like right there, right? But that's not parallel to the total revenue line. So I need to kind of rotate it around until I find a point on the total cost curve where the pen is parallel to the total revenue curve. And that's the point when I bring it in, right, and find that one point where the pen just barely touches the total cost curve. That's going to be the tangent point where the maximum profit is going to happen. So it's going to be roughly, right about there, right? We'll call that QP for Q profit. So how do we find that particular point? Well, that particular point, again, is going to be parallel, right? Is going to have a tangent that is parallel. So I draw these two tag marks here and two tag marks here. That means that this line and this line are parallel. So how do we know if two lines are parallel? Well, two lines are parallel if they have the same slope, okay? So two lines are parallel if they have the same slope. It doesn't matter if they're really close or if they're really far away, right? If two lines have the same slope, then they're going to be parallel regardless of how far or close they are, okay? So, and that's just, so the question is then, how do we find the point on this curve that has the same slope as the total revenue curve? Well, the total revenue curve, we're just going to eyeball it and say, well, the total revenue curve's slope is 75. So the marginal revenue is 75, right? Remember, let's refresh. Marginal revenue is how much more revenue do we get from doing one more visit, one more whatever, scan or test or whatever. In this case, this organization gets an extra $75 for every additional unit of quantity that it does. So that is the marginal revenue. And it doesn't matter whether you're going from 1 to 2 units or from 2,000 to 2,001 units, the organization is always going to get an additional $75. Okay. So now we want to find the slope, we want to find the equation that represents the tangent line where the total cost, where the marginal cost is equal to 75. All right, so we did this problem in the previous video. I'm just going to set that aside for a second. So total cost is 100 plus 10Q plus 1 over 100 Q squared, right? So how do we get marginal cost? Well, we're going to take the derivative, right? So let's do a couple of steps here. What do we do with a constant? A constant goes to 0. We just basically ignore it, right? This 10Q is really 10Q to the 1. So first thing, we bring the exponent down. We multiply it by the constant. Right, bring that down here. Then we bring this whole term down. And we decrease the exponent by 1. So we now have marginal cost is 1 times 10 times Q to the 1 minus 1. Well, Q to the 1 minus 1 is Q to the 0. Anything to the 0 power is just 1. So really we have 1 times 10 times 1, or 10. 1 times 10 times 1 is 10. So we just have 10. And then we do the same thing over here. We take the 2, bring it down. Then we take the constant, bring that down, right? That goes here. Then we bring down the variable, Q2, and we decrease its exponent by 1. So now we have 2 times 1 over 100, that's 2 over 100 or 1 over 50. So I've got 1 over 50 times q to the 2 minus 1. Well, q to the 2 minus 1 is q to the 1. Anything to the first power is just itself, so we can ignore we can stop writing the exponent because that's really just q to the 1. So our marginal cost is 10 plus 1 over 50 q. So going back to our graph, the equation for this line, right, for this tangent line is going to be the marginal cost function, and that's 10 plus 1 over 50q. We want to find where this is equal to or parallel to this. So we want to have the marginal cost at 75 as well as the marginal revenue, because if this is at 75 and this is at 75, then those two lines are parallel. So what we're going to do is we're going to take our MR, which is equal to 75, and we're going to say MR equals MC. And so we're going to say 75 equals 10 plus 1 over 50q. We're going to subtract 10 from both sides, right? So minus 10 over here, minus 10 over here. We'll get 65 equals 1 over 50q. Then we're going to multiply both sides by 50 to cancel out the 1 over 50. And we get q is equal to 3,250. So we start here at 0 and we start moving out away from the y-axis, and we move along the x-axis, the q, and we're increasing quantity. And at some point, we stop losing money at the break-even point quantity, which we didn't calculate, but we could. At the break-even quantity, we start making money, and we keep making more and more money until we get to QP, which we said is equal to 3,250. That is the point where we're going to have the widest gap between the total revenue function and the total cost function. And then when we do the next visit, or whatever this quantity is, the next Q, we're actually going to have less profit because we've moved past the point where we have the maximum gap, and the gap is now starting to close. So with that information, we can actually calculate what the maximum profit that this clinic, let's say it's a clinic, could make. So we would take the total revenue, and we would say the total revenue is going to be 75 times 3,250, and that is going to be 243,750. And they would say, okay, the total cost is going to be 100 plus 10q, and the q in this case is going to be 3,250, plus 1/100th 3,250 squared. So that's 100 plus 32,500, right? So 100 plus 10 times 3,250 is 32,250 plus 32,250 squared. Oh, I got to do that. 32,250, 32. Yep. 3250. It's not 2,250. It's 3250. This is 3250 squared is 10,562,500. But luckily we're taking 100th of it. So times 0.01 gives us 105,625. So 105,625 plus 32,500 plus 100 gives us a total of 138,225. So our total cost is 138,225. Our total revenues were 243. So remember, profit equals total revenue minus total cost. So if we have 138,000 in cost, we make that negative. We add our $243,750 in revenues. We get a profit of 105,525. So that's the maximum profit that this organization could make. Okay. All right, so we did that one. Let's do another one based on what we did in the finding the marginal cost video. So we did one where we said, okay, total cost is 450,000 plus 500 Q plus 1/10 Q squared. How do we calculate marginal cost? Marginal cost, so any constant just goes to 0, right? This 500Q is really 500Q to the 1. So we bring the 1 down. We bring the constant down, 500. We bring the Q to the 1 becomes Q to the 1 minus 1. Oh, marginal cost is really 0. We're going to ignore that. Q to the 1 minus 1 is Q to the 0. Anything to the 0 power is 1. So we have 1 times 500 times 1. So that's 500. And then we do the same thing over here. We bring the 2 down first, we bring the exponent down, then we bring the constant down, 1/10. Then we bring the Q squared minus 1. So 2 times 1/10 is 2/10 or 1/5. Q to the 2 minus 1 is Q to the 2 minus 1 is 1. So that's Q to the 1. Q to the 1 is just itself. So the marginal cost is 500 plus 1/5 Q. Now remember, what we're looking for is, well, this is going to be our total cost curve starting at 450K, right, and going up. And so now we need to know what the revenue function is. Well, let's assume this is fee for service too, and it's going to be $5,000 per unit. So the total revenue is going to be 5,000. So pretty steep number. It's going to go like that, right? Starts at 0 because if you do nothing, you get nothing. And the marginal revenue then is just going to be 5,000. So to find the slope of the point, right, to find the slope of the tangent, that where the tangent is parallel to total revenue, we're going to set, remember, the slope of the total revenue curve is 5,000. So we want to find where the marginal cost is also 5,000 because the marginal cost is the slope of that curve. So I'm going to set marginal revenue equal to marginal cost. Marginal revenue is 5,000. Marginal cost is 500 plus 1/5 Q. And I'm just going to solve for Q. So I'm going to subtract 500 from both sides. I get 4,500 equals 1/5 Q. Multiply both sides by 5 to cancel out the 1/5. And I get a profit maximizing quantity of 22,500. So with a profit maximizing quantity of 22,500, I can now calculate my total revenue is going to be 5,000 times 22,500. It's going to be a really big number. It's going to be I wrote it down. Why did I not see it? 12,500,000. Total cost is going to be 450,000 plus, go back up here, 500 times Q. So 500 times 22,500 plus 1/10 times Q squared. So 22,500 squared. So we get 22,500 squared times 1/10 or times 0.10 is 50 million plus 500 times 22,500 plus 450,000 gives us 62,000. So total cost is 62,325. Sorry, 62,325,000. So profit is total revenue minus total cost. So we have, if we have 62,325,000 in costs, we'll make that negative, and we'll add our revenues. So 500. We get 50,175,000 in profit. Okay. So this point would represent 22,500. The gap would be, in this case, 50,175,000, right? Your total costs would be 62 million, roughly, right? Total revenues would be 112 million-ish, right? And the gap between them is my profit. All right. We'll do one more based on what we did in the marginal cost example, because I want to make one final point. So the last example that we'll do is we had an example where we had total cost was equal to 2,000 plus 20Q plus 1/5 Q squared, right? And so the marginal cost, well, 2,000, it's a constant, so that goes to 0. 20 to Q is Q to the 1, so the 1 comes down, the 20 comes down. Q to the 1 becomes Q to the 1 minus 1. Right, so we've kind of cleaned this up. We've got Q to the 1 minus 1 is Q to the 0. Anything to the 0 is 1. So we have 1 times 20 times 1, which is 20. And then we do the process over here. The exponent comes down first, then the constant comes down, then the Q to the 2 minus 1 comes down. Q to the 2, well, 2 times 1/5 is 2/5. Q to the 2 minus 1 is Q to the 1. Anything to the 1 is just itself. So this becomes Q to the 1 or Q. So marginal cost is 20 plus 2/5 Q. All right, to find the profit maximizing quantity, we need to know what the revenues are going to be. And so in this case, let's assume total revenue is going to be $45 per unit. So for every unit, they're going to earn $45. It doesn't matter where they are on the revenue curve, right? So they're going to go from 0, and it's going to go up at a rate of 45. So their total revenue is going to have a curve of a slope of 45. So the marginal revenue then is just 45. So we're going to try to find the point, the tangent, right, of the cost curve that has a slope of 45. So in other words, we want to find where marginal cost equals the marginal revenue, or marginal revenue equals marginal cost. I like to say it that way. Marginal revenue equals marginal cost. So we want to find where we know what marginal revenue is. It's always going to be 45, so that makes it easy. And we're going to take the equation for marginal cost and plug it in here. And then we're going to solve for Q. So in this case, we're going to subtract 20 from both sides. We get 25 equals 2/5 Q. We need to multiply both sides by 5/2 to get rid of the 2/5. And when we do that, we find that Q equals 62.5. Okay, so the profit maximizing quantity is 62.5. So now we take and we say, okay, well, total revenue then would be 62.5 times $45 per unit. That's going to give us a total revenue of $28.12. And then our total cost is 2,000 plus 20 times 62.5 plus 1/5 of 62.5 squared. So 62.5 squared is 3906, but we only want 1/5 of it. 1/5 is 0.2, right? 1/5 is equal to 0.2. So that's 781.25. We're going to add 20 20 times 62.5. 20 times 62.5. So those added together is 2,031. And then we add the constant 2,000, the fixed cost of 2,000, and we get 4,031.25. So total cost is 4,031. So profit is total revenue minus total cost. So this is our total cost is 4,031. Our total revenue is 2,812. So I'm making the cost negative, and I'm going to add 2,812. Whoop, what went wrong there? Okay, we'll try it the other way. 2,812. Calculator doesn't want to cooperate. 2,812 minus 4,031.25, and you get a loss of 1,219.25. And you say, how is that possible? Well, it's possible that this is, say, 2,000, and the curve just does something like this. In other words, graphically speaking, and so here we're at 62.5, the total revenue curve went up at 45. The total cost curve initially starts out at 2,000, right, and then goes up. And the slope is always 20 plus 2/5 cube. And the problem is that the total revenue, the revenue function at 45 never earns enough money to catch up with the total cost curve. So it never crosses. There is no break-even point. It never catches up the way it did in this first example, right? So in this first example, the total revenue curve starts below total cost, but it goes up at so much of a faster rate that it actually crosses the total cost curve pretty quickly. And then eventually the total cost curve catches up with it and crosses it again. But here, because of the fixed costs are relatively high relative to the amount of profit that the organization can, or excuse me, revenue that the organization can earn, total cost goes up and total revenue never catches up with it. So this organization, the best they can do is minimize their losses at 62.5. So you can see here it's pretty wide, right? And it gets narrower as we approach 62.5. That gap gets narrower. The narrowest point is at 62.5, and then that gap starts getting wider and wider and wider again. So this is the profit maximizing quantity. It's just that the profit, the best profit they can ever do is a loss of $1,200. So the key takeaway, the reason I wanted to do one where there was a loss was to show you that not every business, right? Not every cost structure allows a business to be profitable, to ever have a profit. So in this case, you wouldn't want to do this business. This business would be dead at the get-go, right? Dead at the start, because we wouldn't want to start doing this business because there wouldn't be a way of getting to a point where we're actually making profit. Okay, so you have enough information here now to do the quiz where you practice profit maximization.